Hello everyone, my name is Zahari Dichev and I'm a software engineer at Buoyant, the creators of Linkerd. Today we're going to be doing a deep dive into Linkerd and we're going to focus on the multi-cluster support that has been much anticipated and released recently in 2.8. So the agenda for today is the following. We're going to do a quick overview of what a service mesh is, why you might need one, and how Linkerd works internally. We're going to cover the multi-cluster concepts that governed the implementation of this feature. We're going to look at the architecture and how we designed it. And of course, we're also going to jump into the terminal and so I can show you how using this feature feels like. And then we're going to dive even deeper to track the life of a request across clusters, and I think that's going to be particularly interesting because it's going to give you a bit more deep knowledge into how the whole system has been put together. And then if you have any questions, we're going to have a Q&A, time for Q&A, so you can ask these. So much has been said about service meshes and what this is and why you might need one. And I will try to summarize it with a quote that I think is quite precise and concise in the same way. So in a typical distributed system, naively you might think that the only thing that matters is that A and B can exchange packets. But as your system grows and it becomes more complex, it becomes apparent that this is not the only thing that matters. So what Linkerd gives you is, it gives you the guarantee that A and B can exchange packets in a way that validates the identity on both sides, has clear authorization semantics, is confidential to third parties, and is measurable and inspectable. So to put that in a more diagrammatic context, in your typical distributed system you might have something like this, right? You will have a client that talks to an API gateway which happens to live on a Kubernetes cluster. And when the request hits this API gateway, it's routed to one internal service. And any of these services might talk to a database or hit a Redis cache, or for that matter, talk to a third-party API over the internet. And this is all fine as long as it works. But things start to become a bit more interesting when problems arise. So for example, your database might get locked up, or the data center where it is might be set on fire, or you might deploy a version of your service that is exhibits some sort of a performance regression. So now one of your services is slow, and that reflects on the runtime characteristics of your entire system. Or for that matter, you might lose the connectivity to the outside world and not be able to hit your external third-party API. And when any of these problems arise, you want to be able to make an informed decision, diagnose things quickly so your teams can react in a prompt manner and resolve the problem. But when you have a complex system, that becomes hard. So the way Linkerd solves this problem is by injecting a proxy. So it's a sidecar proxy container and all of your meshed pods, all of your meshed workloads. So now this proxy is running alongside your application containers and all of your traffic goes through it. So instead of looking like that, your traffic pattern starts to look a bit like this. So now all of the traffic is shifted through the proxy. In addition to that, there's the control plane component, which it's rather a set of components, set of workloads that Linkerd runs that you can think of it as a management console for the proxy and for the service mesh in general for Linkerd. So this control plane gives you a few things. So it takes care of issuing and providing TLS certificates for the proxy, because all proxy-to-proxy communication is encrypted by default. It provides service discovery through DNS as well as Kubernetes primitives. It provides service profiles, so you can set rules like timeouts and retries per services. It gives you automatic proxy injection, so there's a proxy injector component that takes care of that. The control plane also ships with a dashboard with a bunch of useful metrics that you can look at in order to reason about your traffic. It also exposes an API interface that a number of CLI commands that we ship with Linkerd use, such as tap, stat, and others. And these allow you to look at real-time statistics about your traffic from the terminal. And then you have the proxy, which is often referred to as the data plane. And that's an ultralight transparent one that's written in Rust. So it's very performant and secure. It has automatic Prometheus metrics export for all HTTP and TCP traffic that goes through it. So the proxy itself exposes endpoints that your Prometheus instance can scrape, so you get data about the traffic that's going through the proxy in Prometheus. It provides latency-aware layer 7 load balancing and automatic TLS out of the box. And what is a particular feature that's actually that I think is pretty cool is that it exposes an on-demand diagnostic tap API. So you can use a CLI to tap into any proxy and see the live requests that are going through the proxy in real time. So oftentimes the question arises, well, how does that proxy end up in my workloads? Well, that's happening through a process that we call injection. So it's usually accomplished by the proxy injector component, which is part of the control plane, but can be done manually as well. And the essence of it is that your pods are modified to include an init container, which is responsible for setting up the IP tables rules for the pod, so all the traffic can go through the proxy. And then there is the sidecar container that runs the proxy itself, intercepting all of your traffic. So if you have to draw that, the injection sort of looks like this. You have your pod running with the application container in there. And then there is an init container at it, setting up the rules. And then there is the proxy as a sidecar container. So now your traffic, your incoming traffic gets shifted. So it first hits the proxy and then goes to the application container. And similarly, your outgoing traffic goes to the proxy first and then to the whatever it's destined to. So when we were so Linkerd is designed around a few core concepts, and that's observability, so being able to collect actionable traffic metrics, security, which is encrypting all of the traffic between services, reliability, which is ensuring that services are available, and traffic management, so routing traffic to services and using advanced patterns such as traffic splitting. So when we were, we kind of thought about all of this, and we wanted to bring these guarantees and these core concepts to the multi-cluster support as well. So you get all of that not only within your cluster, but within your whole ensemble of clusters, so to speak. So this kind of brings the question as to why multiple clusters? Well, there are many reasons that people have pointed out, but most notably it's about traffic management and traffic migration. So people want to be able to do canary deployments across clusters, or be able to use a set of services that are in a pre-prod environment or prod environment for development locally, and make them appear as they are, as if they were in their local kind cluster, for example. As well as also people want to do failover, so kind of shifting traffic from one cluster to another when a certain cluster fails or needs some kind of maintenance. So we kind of thought about all of that, and we decided to have some core concepts across multi-cluster, the multi-cluster feature that kind of build upon the Linkerd's core concepts. And so our solution is secure, and much like with Linkerd, everything happens over MTLS. So even traffic that goes out of the cluster to another cluster, it's TLS. Then we have the solution be Kubernetes first. So remote services, they appear as normal Kubernetes services. So any service that's exported and available in your local cluster, but it's a remote service, it's just a normal service. It's not some kind of special kind of service. And there is no single point of failure. So no single cluster is blessed or magical. Each cluster is running its own Linkerd installation with the control plane. So if a cluster fails, that doesn't bring the whole system down. The solution is also transparent, so applications don't need to know whether a service is remote or local. And the solution is also network independent. So the only requirement is that there is gateway connectivity between clusters, but the underlying network infrastructure or network hierarchy doesn't matter at all. So if we have to draw kind of a diagrammatic representation of what our multi-cluster solution looks like, it kind of looks like this. So imagine you have cluster east and west that you're going to see in the demo in a bit. So these both are running Linkerd. And it's important that Linkerd for both of these clusters is installed with trust roots so the certificates share the same trust root in order to enable the MTLS across clusters. And then you have the Linkerd multi-cluster set of components, which consist of the service mirror, the gateway, and the cluster credentials. And then you have your local services and your remote services that are effectively a proxy to services located on other clusters. So the service mirror is responsible for monitoring the exported state of the target cluster and replicating it. So it would use Kubernetes informers and the Go API client to continuously monitor the set of services that are exported on a target cluster and create proxy services locally. And then there is the gateway, which is responsible for routing incoming traffic to the services, to the appropriate services on the target cluster. So that's that component exposes an external API IP that receives all of that traffic, and then this traffic is routed to where it should go to the internal services in the cluster. And then there are the credentials, which consist of a service account that's located on the target cluster, and it allows the service mirror controller to spin up a Kubernetes API client and monitor the state of this cluster. And then there is a secret that's living in the source cluster, and it's containing the Kubernetes API config for the service account. So this config can be deserialized, and the Kubernetes API client can be spun up. So now, with all of that being said, it's actually pretty informative to do a demo and show you how this feels like and what you can do with it. So in our demo, we have two clusters, east and west. Each cluster has backend service installed, and a test client is deployed on cluster east. So this test client is just a container which we can use in order to curl. So what we want to do is we want to split the traffic to backend service between cluster east and cluster west. So let's actually do that. So here you can see that we have our cluster east with Linkerd installed. What we are going to do is we're going to install the backend service and the test client. We are going to install the backend service onto cluster west as well. And these services respond with a different response, just to be able to differentiate between them. So now you can see that we have the backend service here on cluster east. Now the next thing we are going to do is that we are going to install the multi-cluster components onto cluster east. And that command should install the gateway, the service accounts, as well as the service mirror controller. We're going to do the same thing for cluster west. So now we can see that there is the gateway on cluster east and the service mirror controller. What we want to do now is to be able to provide the credentials that are needed for cluster east to be able to replicate services from cluster west. So we're going to do that with the link command. And what this link command does is that it puts together these credentials. No, that's actually the wrong command. That's the export service command, which is for later. So we are using the link command, which puts together, grabs these credentials and puts them together, the credentials for the service account from cluster west, and packages them as a secret and deploys them onto cluster east. So now we can use the gateways command in order to see that on cluster east knows about a gateway on cluster west that's exhibiting a bunch of traffic characteristics. So this is the latency to this gateway, and it's alive. So there is a probe internally that probes this gateway and informs us whether that gateway is alive at the moment or not. Currently, however, there is no services being mirrored. So what we want to do is we want to export the service from cluster west to be available onto cluster east. And this is done by pretty much adding a few annotations on the service itself. So this command will do that. So now this service is exported. If we look at the gateways now, we can see that now there is one exported services. And if we look at the services on cluster east, we can see that there is a backend service which we know that we deployed, and there is a backend service dash west, which is a proxy for the service that's located on cluster west. So what can we do with that? Well, we can actually SSH into our pod here. And from that pod, we can curl the backend service that's located locally. So it says hello east. And if we curl the backend service that's located on west, we're going to get a different response, right? So now we can step back a bit and think about what we can do. So we can define a traffic split here that splits all the traffic going to backend service in half. So half of the request will go to backend service, which is the local service, and half of the request will go to the service that's located on cluster west. So now that we have that, we can SSH into our test container again and run curl in a loop hitting backend service at port 8888. So you'll see that we now should be getting actually I think I created it in the wrong cluster. Yeah, it's when doing these things, it's pretty advisable to always be explicit about the context. So we are creating that traffic split on cluster east. So now, if we SSH into the container and we run the same command, we see that what's happening is that we get responses from both cluster west and cluster east. And the reason for that is because half of the requests are routed to our local service and half of the requests are routed on to the service that's located onto cluster west. So we can actually look at our traffic split and we can see that both of the services are exhibiting 100% success rate. However, what's interesting to observe is that the latency to backend service west is a bit higher, and that's normal because the service is not located on the local cluster. What's also interesting to see is that we can run the dashboard command now. So that dashboard command gives us the dashboard here. We can look at our traffic splits and get a visual representation of that. And again, you're going to see the characteristics here. So half of the traffic goes to the local service, half of the traffic goes to the service on cluster west. Also, what's also interesting to observe is that we can go into Grafana, and there is a multi-cluster dashboard here that shows you a bunch of traffic statistics about the traffic that's going to remote services. So you can see here that there is a request rate for the Linkerd gateway. So this is for all the traffic that's going to this gateway, no matter the service. But then there is, a breakdown here that's by services, and that would be a bit more interesting if we had more services. But we can see that all the traffic is going to backend service at the moment at cluster West. So this is all quite interesting, and you might ask yourself, well, how does this actually work? Well, the way it's been designed is the following. So imagine you have your client pod that's located on cluster East, right? Well, the moment you fire GET request through curl to backend service, this GET request is actually routed by the traffic split to backend service West, which is the proxy for the service located on cluster West. Now, what's going to happen is that this service, actually, there is no pod behind it. Like, the pod is located on service on cluster West. But what there is that this service has an endpoint that the service mirror has created that has the external IP of the gateway of cluster West. So the traffic will go to that IP on that port. And in order for all of that to happen, however, of course, there is a proxy on this client pod. So this proxy intercepts that request, and it uses the Linkerd destination service to kind of learn a few important things. First of all, it issues a discovery query to the destination service. And the destination service knows that this is the request is going to a service that's actually a proxy for a service located on another cluster. So it's going to return the expected identity of the gateway on the other side so it can enable MTLS. And it's also going to return the fully qualified domain name of the target service on to the other cluster. And that's important because this other cluster might very well have a different cluster domain. And it also is not suffixed with the West, right? The name on the other side is backend service, not backend service West. So when all of that happens, this request, the URI authority is rewritten, the proper TLS identity is set, and this request flies off to cluster West. So once it hits this IP on this port, it's intercepted by this request is intercepted by the proxy, and the proxy will and this gateway will route it to the correct backend service. So, and because all of that, because there is the correct destination encoded in the request, it knows onto where to send it on which port. So, you might be hitting the proxy service onto different ports, and all of that traffic will go to one single port on the gateway, but because we carry metadata indicating which port was actually the original port, we can route it to the correct service. So this is pretty neat. And one other important thing is that because there is a proxy injected into all of these components, like all of your traffic is encrypted end to end. And not only that, but you can also get a bunch of valuable metrics, as I already showed you, about what's happening with the traffic across clusters. So that being said, this was sort of the first iteration of the multi-cluster support that we designed, and it works quite well. However, there are a few improvements that we have in mind and we are actively working on at the moment. So first of all, now there is a service, we want to be, and now there is a single service mirror controller running, and it's responsible for pretty much all the linked clusters. We want to split that up and have a service mirror controller per target cluster. And I think that's going to simplify things greatly and make the kind of the cognitive luggage lighter. And it's going to be much easier to debug whenever problems occur. We also want to introduce a CRD to better represent the target cluster information. So now a bunch of that information is encoded in a secret. Other bits of that information is encoded in arbitrary annotations on the services that are mirrored and whatnot. We want to consolidate all of that into a CRD that represents this information, so it's all in one place. We want to support traffic policy and much finer grained permissions control as to what traffic can go where. And of course we want to support plain TCP traffic. So this is something so currently it's all HTTP. We want to support plain TCP across clusters, and this is part of a larger refactor and larger piece of work in the proxy, but we have an idea of how to do that, and work is actively happening at the moment. So this is something that's going to be coming out soon. So with all of that said, I'm happy to answer any questions if you have one. And as always, you can go to my GitHub account and take a look at my repo that contains the talk, so you can look at the slides again. Thank you a lot for your time.